was that the entropy of a black hole was supposed to capture the information lost when the black hole was formed. He interpreted it as the logarithm of the number of states the black hole could have formed from. And he proposed a generalized second law, which said that the generalized entropy was supposed to always increase, or at least never decrease. So S out was supposed to be the ordinary entropy of matter and radiation outside the black hole. And I think for this, Bekenstein intended thermodynamic entropy. And anyway, this combination was supposed to be the generalized entropy. And it certainly isn't constant in time, because when you toss the cup of tea into the black hole, it increases by quite a bit. So this has got to be a thermodynamic entropy. So the claim was that when something falls into the black hole, S out may go down, but A over 4G H bar increases by more. So the generalized entropy increases when something irreversible happens. So the cup of tea falling into a black hole is irreversible. And ordinarily in thermodynamics, the thermodynamic entropy increases when something irreversible happens. So in an irreversible event, the generalized entropy was supposed to increase. Now, Bekenstein made a few tests of the generalized second law, of which I'll describe the most important one. And you'll see it didn't completely work. So you shine photons with a wavelength lambda, and therefore energy E equals 1 over lambda on the black hole. The entropy of a single photon is of order 1, for example, because the photon has two polarization states. When the black hole absorbs one photon, its mass shifts by 1 over lambda. So its entropy shifts by something we can work out, and assuming m is much bigger than 1 over lambda, the entropy shifts by roughly this much. Now, Bekenstein wanted the increase in the entropy of the black hole to be more than the reduction of the outside entropy, which is of order 1. And he observed that if the black hole is capturing a photon of size smaller than the Schwarzschild diameter of the black hole, say lambda much less than 4gm, then delta S of the black hole is much more than 2 pi, which is satisfactory. It gives delta S bigger than 1. So as long as you're shining on the black hole photons whose wavelength is less than the black hole size, everything was fine. There actually was a problem if you read Bekenstein's paper. He didn't have a satisfactory answer if the black hole is absorbing photons of wavelength larger than the black hole size, which can happen, although not very efficiently. The black hole can certainly absorb photons of any wavelength. And the problem is that a very, very big photon still has an entropy of order 1, but it has an extremely small energy. So you can make the shift in energy of the black hole as small as you want, and therefore the shift in area as small as you want, keeping the entropy that the photon carried fixed. And I would say if you read Bekenstein's paper, he didn't have a satisfactory answer to that. In hindsight, the question doesn't have a satisfactory answer in the framework that Bekenstein assumed, which was that whatever falls behind the black hole horizon stays there forever. In thermodynamic terms, since Bekenstein assumed that the black hole does not radiate, you'd have to assign it a temperature of 0. But then thermodynamics says that at equilibrium, changes in energy and entropy are governed by dE equals T ds, or ds equals dE over T. So a system with T equals 0 should have ds equals infinity if dE is supposed to be not 0. And Bekenstein talked about assigning a temperature to a black hole, but he clearly didn't really believe it, as you'll see if you read his paper. So in that framework, there wasn't a satisfactory answer to the problem of the black hole absorbing a photon of very long wavelength. Now, well, famously, Stephen Hawking, a couple years later, solved this problem and also confirmed the general idea of Bekenstein as being correct by showing that quantum mechanically, a black hole is not really black. It has a temperature proportional to Planck's constant. As preparation for explaining what Hawking did, I want to recall the idea of a Penrose diagram as a convenient way to depict and visualize spacetime. So here, I've just sketched the Penrose diagram of Minkowski space. So what's a Penrose diagram? It's a diagram where time runs vertically, space runs horizontally. Spherical symmetry is usually assumed in drawing the Penrose diagram, and angular coordinates are suppressed. So space is depicted as being one-dimensional from left to right. So the radius is 0 on the left, and it's infinite out on the right of the picture. But there's one more crucial trick due to Penrose. In drawing such a diagram, it's very convenient to make a conformal mapping so that you can see spatial infinity. So distances have been compressed conformally in such a way that this is spatial infinity, this is future infinity, this is past infinity. These diagonal lines are called null infinity. They're the regions that an outgoing light ray would reach after propagating indefinitely in time. And the diagram is usually drawn so that the speed of light is 1, and therefore an ingoing or outgoing light ray travels at a pi/4 angle to the vertical. I think I have one on the next page, right? So in drawing a Penrose diagram, we usually draw it so that a radial ingoing or outgoing light ray, this should be pi/4, is at a pi/4 angle to the vertical. So the purple line, which is meant to be at a pi/4 angle from the vertical, is supposed to be an outgoing light ray. So that's Penrose's way of depicting Minkowski space. An outgoing light ray will eventually end somewhere on this line. An incoming light ray would have begun somewhere on this line. Spatial infinity is out here, and a massive particle will have been born here and will end up there in the far future. That, in a nutshell, is Penrose's way to depict Minkowski space. Now, here's the analogous picture of a black hole spacetime, which Hawking used in making his discovery. So first of all, the spacetime isn't empty. So here, this was empty. I just drew a picture representing Minkowski space. The spacetime isn't empty. The portion of the spacetime filled by a star is shown in red. And part of the picture is the same as it was before. So past null infinity, to be more precise, is this diagonal line. Spatial infinity is this point, and future null infinity is here. But the difference from the previous picture is that future infinity in Minkowski space was at the top of the picture. But in the black hole spacetime, future infinity is up here, and an observer at future infinity can't see the whole spacetime. Since light rays would travel at this pi/4 angle to the vertical, you can only see the part which is to your past, which is the interior of this trapezoid. And there's that whole triangle up here that you can't see. That's the region behind the horizon, which is this diagonal line, which is meant to be at a pi/4 angle to the vertical. It hasn't been drawn extremely carefully. The horizon is the trajectory of an outgoing photon that doesn't quite escape. Well, it ends its life at this future infinity point. If you're behind the horizon, you end up at the singularity, which is that wiggly line at the top. So the picture is a lot like the previous picture from Minkowski space, except that from the far future, you can't see the entire past of the spacetime. From the far future, you can't see the whole spacetime, only the part outside the horizon. So a physicist, an experimentalist, making observations would be collecting outgoing radiation from the black hole somewhere along this black line, and observations in the far future would be made up near this corner. Now, the crucial thing is that measurements that an observer can make at future null infinity can be traced back to initial conditions of the quantum field on a Cauchy hypersurface. A Cauchy hypersurface is just a space-like hypersurface, and I've drawn one in blue. So the blue curve represents a space-like hypersurface. It's space-like because it's always at an angle from the horizontal that's less than pi/4. And I could have drawn a space-like hypersurface that went straight across left to right, but I chose one that intersects the horizon to the future of the collapsing star. in the vacuum region, the white region, not in the interior of the star, which is red. So we can choose this Cauchy hypersurface as we wish. It can intersect the horizon far to the future of the collapsing star, where the quantum fields are essentially in the vacuum, which will make the analysis simpler in a moment. Now, this picture shows signals propagating out at the speed of light from the initial value surface to the observer at infinity. So somewhere on future, what I'm calling here future infinity, is an observer who's watching. The observer watched the star collapse to the black hole, and now, a month after the black hole formed, the observer is watching to see if the black hole is truly black. So the observer is collecting possible radiation that might emerge from the black hole. Well, if radiation does emerge, it'll be collected up here, and it could be traced back to initial conditions on this blue hypersurface. Of course, it could be traced back even farther back in time, but if we do that, we'll get to a region where the space-time is less simple. As you'll see in a moment, it's better to only trace back the radiation to a region that's sufficiently far in the past of the observer, but also sufficiently far to the future of the collapsing star. We'll see in a moment exactly what we need. So what will the observer see? Part of Hawking's insight was that although the full details of exactly what the observer will see depends on the details of the collapsing star, if you ask what the observer will see in the far future after transients die down, there's a universal answer. The important point about this picture is that a signal that is received very late means very close to future infinity, this corner of the picture here, originated from very close to the horizon on this blue hypersurface. So it'll be important in a moment to take into account the way distances in space and time were stretched conformally so that we could see the picture in this nice picture. But because the very late observations originate from very close to the horizon, that means that observations at late time depend on measurements of the state of the quantum fields at short distances. This sentence is actually the key to Hawking's discovery. So since that sentence is the key, I'm going to explain it in some detail. And then the fact is that every state is equivalent to the vacuum at short distances. So Hawking discovered that what the observer up here measures at late times amounts to probing the vacuum state at short distances. That's why he got a universal answer for the late time behavior, regardless of exactly how the black hole formed. So I'm going to draw a picture that, I've redrawn the important part of this picture. Here there's a lot of stuff. There's the collapsing star, there's spatial infinity, there's a complete Cauchy hypersurface, there's the past, there's past null infinity, most of which is irrelevant for the observations of the future observer. I'm going to redraw the picture showing only the part that matters. The part that matters is a little bit of the Cauchy hypersurface, now drawn in red, outside the horizon, and that there's the time t of the future observer. T goes to infinity up here. The observer is making observations at late times. And then these purple lines, which are meant to be at a pi/4 angle from the vertical, are light rays that describe outgoing massless photons propagating to the observer at the speed of light. Now, U is a measure, so T is the time at which a signal is detected by an observer at infinity. And U is the distance from the horizon at which the signal originated. You can find the relation between U and T by solving for the geodesic equation in the field of a Schwarzschild black hole. So if U is 0, that would mean you're on the horizon, and you'd never escape, or if you like, you'd escape at t equals infinity. As you'd never escape at any finite time. If U is very small, you eventually make your way out of the field of the black hole, but it takes a long time. The signal that comes from U equals epsilon, where epsilon is very small, will eventually escape to the observer at infinity, but at an extremely late time. And the key formula which shows how late the time is that as u goes to 0, the time at which the signal arrives to the observer at infinity diverges logarithmically as 4gm times the log of 1 over u. So that's the key relationship which in a moment will lead us to Hawking's big discovery. And we get it by just solving for the equation of a null geodesic. Well, if you use the Kruskal-Sakaras coordinates for a black hole, you don't even need to solve the geodesic equation. Because in those coordinates, the geodesic is just described by u equals constant. Then all you need is the change of variables from u to Schwarzschild coordinates. If you're working in Schwarzschild coordinates, you have to solve the geodesic equation to get this relationship. Now, instead of writing this as a relation for t in terms of u, we can write it as a relationship for u in terms of t. That's informative because the observer who's making the observations knows the time at which the observation is made. But it takes theory to know what is the position near the horizon from which the signal came. So from the observer's point of view, you look at your watch to measure t, and you solve the geodesic equation to know where the signal came from. And this formula shows you that if t is large, then u is extremely small. And t doesn't have to be very large. For example, at the LHC, people try to probe the vacuum at short distances. They get down to 10 to the minus 16 centimeters, or 10 to the minus 17 centimeters, roughly. Now let's do this for a Schwarzschild black hole with the mass of the sun. So 4gm for the sun is milliseconds. So suppose t is 1 second. Then t over 4gm is hundreds. And this is e to the minus hundreds, much less than the distances probed at the LHC. So for a black hole with the mass of the sun, if you wait till 1 second after it collapses, you're probing the vacuum at a distance that's unbelievably less than the distance at which the LHC probes the vacuum. And if you're not satisfied with that, you can wait 1 more second, and you gain another factor of 10 to the hundreds. So by making measurements at so-called late times, you're probing the vacuum at distances that are unimaginably small compared to the distances we probe it in any other way. Now, what will happen if we probe the vacuum at such short distances? Another important fact is that u dt is exponentially small as well as u being exponentially small. So that means a mode observed at infinity had very, very high frequency near the when it was created. And therefore it was propagating freely. That was why we can think of it, that was why Hawking was able to use geometrical optics. So a mode of any given energy that we observe at late time, which means, let's say, after 1 second for a solar mass black hole, originated from a very high energy mode near the horizon. That's why there's a simple answer. So the observer measured at infinity probes the radiation by measuring a quantum field psi of t. And a typical observable is a 2-point function. And typically when you probe the vacuum at short distances by a quantum field, you get a power law singularity. So I've written a power law with a single pole, power of 1, for a free Feynman with dimension half in the 1 plus 1 dimensional sense. For a boson, like the electromagnetic field, the power would be 2 instead. Setting u equals a constant times e to the minus t over 4gm, we see that for the observer at infinity, the 2-point function of psi of t prime is this. All I did was to take the vacuum excitation value of a free field, and I converted it to what the observer at infinity measures by saying that u is e to the minus t over 4gm. So I've literally taken the 2-point function that's observed is the 2-point function in the vacuum with this change of variables. Roughly all that happened was that u turned into the exponential of t, except you have to worry about what happens to du and du prime and u minus u prime. But to go from here to here is literally just a change of variables. The change of variables being this one. So you plug that change of variables into this formula, and you get this one, which describes the measurements of the observer, although those are the measurements in case what are being observed is a fermion. And we see that this is anti-periodic in imaginary time, meaning it's odd under shifting t to t plus 8 pi gm times the square root of minus 1. Well, anti-periodicity in imaginary time for fermions, or periodicity for bosons, is the hallmark of a thermal correlation function. So this computation is how Hawking discovered that the observations of the observer at infinity would be thermal. The observer at infinity would see thermal correlations. And the antiperiodicity corresponds to a thermal correlation function at a temperature 1 over 8 pi gm, which is the Hawking temperature. In other words, at a temperature 1 over 8 pi gm, you get periodicity in imaginary time with this period, periodicity or antiperiodicity with this period for bosons or fermions, which is what Hawking discovered. So in other words, a black hole, after transients that depend on how it was created dies down, radiates thermally at a temperature 1 over 8 pi gm. So that explains why Bekenstein had trouble making sense of the interaction of the black hole with very low energy photons. The photons he had trouble with were the ones whose wavelength was bigger than the Schwarzschild radius of the black hole, but that means that their energy is less than the Hawking temperature. And that means that the black hole is emitting many such photons, more than one in each mode. And therefore, you can't sensibly study the absorption of such photons by the black hole without taking into account that they're being strongly emitted by the black hole. We can also now confirm Bekenstein's ansatz that the black hole entropy is proportional to the area and determine the constant. Using dE equals TdS, and taking E to be m for a Schwarzschild black hole, and the temperature to be what we just computed, 1 over 8 pi gm, gives ds equals 8 pi gm dm, so the entropy is 4 pi gm squared. But we computed before that the area was 16 pi g squared m squared. So we get Hawking's refinement of Bekenstein's formula. The entropy of the black hole is the area over 4G. So that's how Hawking confirmed Bekenstein's ansatz and determined the constant that Bekenstein didn't know. Now, ever since this period, many researchers have thought that somehow the entropy A over 4G means that the black hole can be described by some sort of degrees of freedom that live at its surface, 1 bit or qubit for every 1 over 4G of area. For example, in a famous article in 1992, John Wheeler illustrated the idea with this picture, where he visualized the black hole horizon divided in units of 1 over 4G of area, and on each unit he placed a 0 or 1, which I hope you can see, which is supposed to represent the value of a bit. But if you read the article, you'll see that his bits are supposed to be values of what are now called qubits. The term qubit hadn't been invented yet in 1992, I don't believe, so he couldn't call them qubits. But anyway, there was 1 bit or qubit for every unit area on the black hole horizon in this picture. The trouble is that no one has really given flesh and blood to this picture. It's just a picture people like to draw. Wheeler published this picture in this article. I tend to believe he'd been drawing it for a long time before. Now, Hawking's approximations assume that the radius of the black hole is much bigger than the Planck length. So, for example, take a solar mass black hole with an initial mass of order 10 to the 33 grams. It has a Schwarzschild radius, which is a few kilometers, so a few times 10 to the 5 centimeters, much bigger than the Planck length. It'll shrink down to a mass of order 10 to the minus 5 grams before Hawking's approximations break down. So for a very long period, while the solar mass black hole radiates away almost all of its mass, Hawking's calculation is reliable. We don't really know what happens at that point, but we presume that eventually the evaporation ends and we're left with stable elementary particles. Now, a fundamental point about Hawking radiation is that the radiation appears to be thermal, even though the black hole could have formed from a pure state. And even though the black hole it depends on, most probably the black hole didn't really form from a pure state, because even if you believe the whole universe was in a pure state, the black hole formed from matter that had interacted with other matter. So by itself, it was probably in a mixed state. But regardless, the black hole did form from matter in a low entropy state. For example, I remarked that the thermodynamic entropy of the actual sun is 10 to the minus 20 of its Bekenstein-Hawking entropy. So even if the sun formed from matter whose von Neumann entropy equaled the thermodynamic entropy, the most it could be, the sun definitely is in a low entropy state and formed from a low entropy state. So the actual sun is in a low entropy state in the units we're talking about. So if a star with a mass not too different from that of the sun, and therefore also in a low entropy state, collapses to a black hole, that black hole did form from a low entropy state, from a state with entropy much less than the Bekenstein-Hawking entropy. So there's a puzzle that the Hawking radiation appears to be thermal, even though in the real world, black holes are formed in low entropy states. That's presented a puzzle ever since Hawking's discovery in 1974. It's driven much of the research in this field, and to this day it's only partly resolved. Hawking's approximations are valid for almost the whole evaporation process, and appears to show that the outgoing state is thermal, ultimately with a very large entropy, which is of order 10 to the 76 for a solar mass black hole, roughly 10 to the 20 times the entropy of the actual sun. But if the formation and evaporation of the black hole are described by the ordinary laws of quantum mechanics, then if the initial state is pure, or more generally, if it's of low entropy, as in the real world, the final state should be pure or of low entropy. And as I say, that's some aspects of that are better understood today, but not entirely. Concretely, the reason that the Hawking radiation seems to be thermal, even if the black hole is in a low entropy state, is that the observations of the distant observer amount to observing the quantum fields only outside the horizon. So that's the essence of the Hawking effect. So even if the quantum field, the vacuum state of a quantum field in all of space-time is a pure state, and in general you might assume that the quantum fields throughout space-time are in a low energy state or possibly a pure state. But in the calculation that Hawking did, remember the key fact was that making observations at late times, sorry it's taking so long, maybe I shouldn't have scrolled back through all this. Making observations at late times amounted to looking very close to the vacuum, quantum fields in the vacuum, but only outside the horizon, not behind the horizon. And even if the quantum fields in the whole space-time are in a pure state, observing them only outside the horizons means that, well, the fields only outside the horizons are effectively in a very mixed state. That is a basic interpretation of the Hawking effect. Sorry. Next time I'm not going to scroll backwards through all this. Sorry. So anyway, the essence of the Hawking effect is that observing the quantum fields only in part of space-time means you'll be observing a mixed state. Let's remember how that works in ordinary quantum mechanics. We start with a pure state psi AB in a tensor product Hilbert space with two factors, HA and HB. First, we make the pure state density matrix. Rho AB is the projection operator onto some pure state psi AB. The expectation value of any operator OAB, the expectation value of the operator in the state is the same as the trace of the operator times the density matrix, just by taking the bra from the left and moving it over to the right. as part of the operator. So rho AB here is an orthogonal projection operator onto a pure state. In particular, it's Hermitian and non-negative, and its trace is 1. It also has rank 1. Now suppose we're only going to observe the subsystem A. In quantum mechanics, that means we only consider operators of the form some operator on system A times the identity on system B. Well, for such an operator in the state psi AB, well, in general, for any operator, its expectation value would be the trace of the operator times rho AB. But here we look at an operator of this kind. It's the identity on system B, and that means we can take what's called a partial trace over system B and reduce to a density matrix of system A only, gotten by taking the trace over the degrees of freedom of B, or rho AB. What that means is that we sum over the unobserved states of system B because we're only planning to observe the states of system A. And then we can describe our observations by a density matrix of system A only. So for measurements in system A only, we can use the density matrix rho A that we got from rho AB by taking a partial trace on HB. System A then has a von Neumann entropy that in this case is called entanglement entropy because it arises entirely from the entanglement of system A with system B, the overall state being pure. Now, the idea that black hole entropy should be understood in such terms was apparently first put forward by Raphael Sorkin in 1983 in a paper that didn't initially attract much attention. The idea was the following. In quantum field theory, divide space into two regions, A and B. Let psi be the vacuum state in the whole universe, a pure state. Let rho A be the reduced density matrix of the vacuum for the state psi. The density matrix you would use if you're only going to make observations in region A because you've taken the trace over the degrees of freedom in region B. Of course, in our application, region B will be the region behind the black hole horizon. Region A will be the region outside. One can try to calculate the entanglement entropy SA, and that's what Sorkin did, and in more detail later in a paper also with Bombelli and, I apologize to a third author, I'm forgetting. In doing this, they found that this entanglement entropy is ultraviolet divergent, but the coefficient of the divergence is proportional to the area slanted A of the boundary between regions A and B. So Sorkin's idea in modern language was that somehow gravity cuts off the divergence, the ultraviolet divergence, replacing A times infinity, which is the answer without gravity, by the Bekenstein-Hawking answer, A over 4G. So that was the intuitive conception, which is somewhat better understood today, and I'll mention in a moment one of the later insights, but it's certainly, the picture is not fully available. But this makes a lot of intuitive sense as it matches two ideas. One is that A over 4G is the irreducible entropy of the system for someone who has access only to the region outside the horizon. That's a restatement of Bekenstein's original idea, I guess. Two, the divergence in the entanglement entropy is proportional to the area. Thus the divergence Sorkin, and in more detail Sorkin and his collaborators found, because it comes from short wavelength modes near the horizon. As if, after cutting off the divergence, the density of quantum degrees of freedom on the horizon is 1 over 4G per unit area, as in Wheeler's picture. So Sorkin's idea matches these intuitions about what the black hole thermodynamics means, but as I say, it's definitely not been fully fleshed out and turned into a real theory even today. There was, however, one more observation of what I'll call the classical period. What I'm about to tell you is the last observation of what I regard as the classical period, and then I'll jump ahead and explain one of the ideas of the modern period, hoping I haven't prevailed on you too much, hoping I'm not going too much overtime. So to restate what I said, Sorkin reinterpreted S out. S out of Bekenstein had been the entropy of ordinary matter and radiation outside the black hole. And he was vague about what he meant by entropy, but reading his paper, it looks like he had in mind ordinary thermodynamic entropy. And that would make sense with the fact that he was aiming to understand the second law, which is a statement about thermodynamic entropy, not von Neumann entropy. But Sorkin reinterpreted it S out as being the von Neumann entropy of the quantum fields outside the black hole. As was shown shortly afterwards, not that shortly afterwards, it was shown a decade after Sorkin by Susskind and Uglum, if you reinterpret S out in the way that Sorkin had suggested, then the generalized entropy of Bekenstein is better defined than either term is separately. So the second term has the ultraviolet divergence that Sorkin noted. But the first term has a similar problem because there's an ultraviolet divergence in the relation between the bare Newton constant G0 and the physical observed Newton constant G. So in the Hawking paper where he discovered black hole evaporation, he didn't calculate loops that renormalize Newton's constant. So presumably, although he didn't really say so, the Newton's constant in his paper was the bare Newton's constant. On the other hand, if we talk about the real world, when we talk about Newton's constant, we mean the physical Newton's constant. So to go into more detail, we have to discuss the comparison between the bare Newton's constant that Hawking used and the physical Newton's constant that we use when we talk about the sun in the real world. Well, the relation involves an ultraviolet divergence, and at the one loop level, it takes this form. And at the one loop level, the constant is independent of h bar. And Susskind and Uglum argued that the ultraviolet divergences in S out cancel those in 1 over G, so that the combination is ultraviolet finite. And they showed this at some level, and later authors have improved this derivation. And this claim is, although some aspects could still be questioned, this claim is basically pretty well established by today. So that's one fundamental insight. The generalized entropy is better defined than either term is separately, from a quantum mechanical point of view. So 21st century developments have supported these ideas, though leaving us with plenty of mysteries. And I'm going to use the remaining time to try to explain something of the modern perspective. So as I've explained, black hole thermodynamics originated with the mysterious claim that the purely geometric quantity A over 4G can be interpreted as an entropy. As I stressed, this is a thermodynamic entropy which is believed to obey a generalized second law. It's got to be interpreted as a thermodynamic entropy because it increases when the black hole absorbs matter. I've also emphasized that the other side of entropy is the purely microscopic von Neumann entropy, minus the trace of rho log rho. In general, the relationship between the microscopic entropy and the thermodynamic entropy is an inequality. They're equal if a state is as random as it can be given macroscopic observables. But if a state is a pure state or a low entropy state masquerading as a mixed state, it looks thermal for all practical purposes, but if you know all the microscopic details, you'd know it isn't. In that case, the von Neumann entropy is less than the thermodynamic entropy. So is there a geometric or gravitational formula for the von Neumann entropy? Well, in fact, there is such a formula. The first version was discovered by Ryu and Takanagi, with later refinements by several groups. I'll try to motivate the Ryu-Takanagi formula, and that's basically the last thing I'm going to explain today. Well, here's the simplest solution of Einstein's equations that describes the black hole. Actually, I had it also at the beginning of the talk. It's the Schwarzschild solution. And in this form, it describes the geometry outside the black hole horizon. It's a good solution if R is bigger than 2gm, the horizon radius. So it describes the gravitational field exterior to any body that's spherically symmetric, such as the sun to high accuracy. But if a spherically symmetric body undergoes gravitational collapse to a size less than 2 gm, the solution is incomplete because it has a singularity at 2 gm. But various researchers discovered in the 1950s and 60s that this is only a coordinate singularity and the solution can be continued to r less than 2 gm. Now, I'm going to draw a Penrose diagram that describes that, but I'm not going to fully explain it. I'm hoping many of you have seen it before, and the others will hopefully be comfortable at imagining it. So when you learn to extend the solution past the horizon, you get what's called the maximally extended Schwarzschild solution, and it's quite remarkable. It describes two asymptotically flat worlds connected by a wormhole. The wormhole is sometimes called an Einstein-Rosen bridge, as Einstein and Rosen discovered part of this picture in the 1930s. I've drawn a cartoon version depicted via a Penrose diagram, but in drawing this cartoon version, I've assumed a small negative cosmological constant that provides a sort of infrared cutoff. I did that because it will make the explanation in the next few minutes easier. So if we were in an asymptotically flat spacetime, the picture would go out as a diamond. But there's an infrared cutoff that's very convenient. It's been discovered in the last 25 or 30 years that a lot of studies of gravity are simplified by this infrared cutoff of assuming a small negative cosmological constant. And then there's a sort of time-like boundary where the observer lives, and there are two kinds of observers, one on the right boundary and one on the left boundary. They actually can't communicate with each other. So the left and right boundaries are entangled in the quantum mechanical sense. But although this baffled and puzzled Einstein, Podolsky, and Rosen, who claimed it was a paradox, quantum mechanical entanglement doesn't enable us to exchange information between two sides. It does give correlations between measurements. So in the classical picture, the left observer can't communicate with the right observer because, you see, a signal traveling at the speed of light will go at a pi/4 angle from the vertical and will end at the future singularity. So the left observer can try to send a signal to the right observer at the speed of light, but will fail. The signal will end at the right of the singularity. So the geometry correlates the two sides in a way that's somewhat analogous to quantum entanglement, where two systems are correlated, but not in a way that enables you to exchange information. Somehow, the two-sided nature of the maximally extended Schwarzschild solution is a geometrical realization of quantum entanglement. Now, the part of the space-time that our right observer can see and influence is shown in red. The right observer lives here at the right boundary of the space-time. The right boundary is a region at infinity, far away from the black hole. Then if you went through the wormhole, well, first of all, you can't go through the wormhole. You'd have to travel horizontally in the picture. Only a tachyon could go through the wormhole. If you travel slower than the speed of light, that means at an angle from the vertical less than pi/4, you'd end at the future singularity. But if you could go faster than light and go through the wormhole, you'd reach eventually the left observer in the other asymptotically flat region. The region of the space-time that the right observer can see and influence is shown in red. You can see the region to your past, so the region that can communicate with the right boundary at less than a pi/4 angle to the vertical is this triangle, and that's the same region that you can influence. You can send a signal from here, anywhere in that right triangle. You can also receive one. Likewise, the left observer can see and influence the blue region. These regions are bounded by past and future horizons, which are the diagonal lines in the picture, where the triangles end. Those lines are all meant to be at a pi/4 angle from the vertical, although all this was drawn by hand, not very precisely. As understood by Hartle, Hawking, and Israel in the 70s and reformulated later by Maldacena, in this universe there's a natural pure state, the thermal field double, that to an observer on either the right or left looks exactly thermal at the Hawking temperature. And according to Bekenstein and Hawking, the entropy of this density matrix is the horizon area. And for this ideal solution, it doesn't matter what horizon one picks or where one measures it. But for what I'm going to tell you, we're not particularly interested in that particular state. We want to look at all kinds of states. So we're going to discuss some other states, and that's why I'm not going to go into much detail about this very special state of Hartle-Hawking in Israel. We're going to discuss general states, and we imagine two observers, one lives on the left, one lives on the right, and they decide to disturb the system. And they're going to disturb it by applying unitary operators, which is all you can do to a quantum system. So first I'll describe it abstractly. Here we have a two-sided system AB, where A and B represents the left and right exterior regions of the spacetime. We have a pure state that might be the Hartle-Hawking Israel state, psi AB. So the combined system has a pure state density matrix, but on the left and right, there are thermal density matrices that you get by tracing out the right or the left. The left observer can manipulate the system by applying a unitary operator UA on the left side. The right observer can manipulate the system by applying a unitary operator UB on the right side. The left observer on the left side, the right observer on the right side. What happens to the geometry when the left or right observer applies a unitary transformation? Well, for example, the right observer could create particles that head into the interior. Assuming they're massless particles, they might fall in at the speed of light at angles pi/4 to the vertical. So I've drawn blue lines at a pi/4 angle to the vertical, but you could have thrown in massive particles that would travel more slowly and closer to the vertical. But the picture is time symmetric, so the right observer can also create a state that had additional particles in the past. So here's a cartoon picture of a more general state that the right observer might create, starting with the original state. Now, when I say the right observer can throw in particles, the particles could also be macroscopic objects like tables and chairs. Now, throwing in tables and chairs increases the black hole mass and therefore the horizon entropy, so it increases the Bekenstein-Hawking entropy. So we'll get a new state where this thermodynamic entropy will be different, and in fact will be bigger. Concretely, what will happen is the following. In the new state that the right observer creates, the geometry is different. It's still the Schwarzschild solution to the left of all these blue lines, but to the right of the blue lines, you have to take into account the gravitational field due to the blue particles, and the metric would be a different one. And the horizon would also be different. The horizon would no longer be the old horizon, these black lines. The horizon would be somewhere farther to the right. But I didn't try to draw that realistically. I haven't tried to draw the new horizon. But the new horizon will definitely be to the right of the old horizon, because the gravitational field of these new particles contributes mass to the black hole and makes the horizon area more and moves the horizon outward. So as I said, I did not try to draw the picture realistically to show the new horizons. Now, while the right observer is manipulating the state, the left observer can do the same. So the left observer can create all kinds of particles that go into the past or the future, schematically drawn by these red lines, which I again took to be all at more or less pi/4 angle to the vertical, although it could have been at a smaller angle to the vertical. So the left and right observers can really modify this space-time in a lot of ways. But one thing which we know is that they can't change they can change the state a lot. Abstractly, what they can do is apply a unitary operator on the left times a unitary operator on the right. And those unitary operators can be chosen arbitrarily. So starting with the state psi AB, you can make all kinds of states. And there isn't too much that you can't change. But there are a few things you can't change. And one thing that they can't change is the entropy. Because acting with UA and UB will change both rho A and rho B by unitary operators. So it will not change the von Neumann or entanglement entropy between the two sides. So the von Neumann entropy, unlike the thermodynamic entropy, these observers cannot change despite all the tables and chairs and elementary particles that they throw in or remove. So if von Neumann entropy can be represented by something in geometry, it's got to be something that they can't change. So we can ask, what is it in this space-time that the observers can't manipulate? Well, there's only one place in the whole Penrose diagram. In the Penrose diagram, there's only one point that they can't change. You have to remember that the angles are suppressed. So there are two angular variables, and therefore this point represents a two-sphere. But in the picture, the only point that the left and right observers can't do anything to is the bifurcation surface, it's called. The point where the diagonal black lines that used to represent the horizon meet. Because the infalling blue lines and going to the past and future can intersect, well, can reach anywhere to the right of this diagonal, and the red ones can intersect, they can reach everywhere except in the left corner of the picture. The red ones can reach everything except the right corner of the picture. And together they can reach everything except that one point. So if there is a von Neumann entropy of this space-time, it's got to be represented by the geometry at the bifurcation surface, which used to be the horizon. Now, since the picture has become rather busy, let's go back to where we started. Here's the original space-time, and I've drawn the bifurcation surface. The one point that can't be manipulated, the one point in the picture, meaning the 1-2 sphere, that can't be manipulated by the left and right observers. The only place they can't change the geometry is the bifurcation surface where the two horizons cross. So it's natural that the von Neumann entropy should be the area of this surface if it is any kind of area. In the formula for von Neumann entropy, we shouldn't refer to the bifurcation surface as the horizon, because once the space-time is perturbed on the left and right, the surface is not a horizon any longer. In fact, the two observers have different horizons. The horizon for the right observer moves outward to the right. The horizon for the left observer moves outward to the left. And the bifurcation surface is in the new space-time is in a no man's land between the two horizons. But what you can say about that surface is that although it's no longer a horizon, it's what's called an extremal surface. That means a surface whose area is stationary among all nearby surfaces. And it remains extremal in the more general space-time that left and right observers can create by their manipulations. This follows from the Einstein equations. So the idea of Ryu and Takinagi in the type of example I've been describing, which actually wasn't their original example, is that the von Neumann entropy of the left or right observer is the area of an extremal surface that separates the two observers, divided by 4g. Compared to the thermodynamic entropy, which is given by the horizon area over 4g, where each observer would have a different horizon and a different horizon area, so each observer would see actually a different thermodynamic entropy. But the von Neumann entropy doesn't change, and it's the extremal area over 4g. So this is the modern understanding, except I've given only a special case of the explanation, but this is the modern understanding of the analog for von Neumann entropy of the Bekenstein-Hawking entropy for thermodynamic entropy. Both formulas have quantum corrections, which is why I've written wiggly lines rather than equal signs. You can use Einstein's equations to prove that the extremal surface is always behind the horizon, and that, in fact, the von Neumann entropy given by this formula is always less than the thermodynamic entropy, which, of course, agrees with expectations. Based on, as I explained at the very beginning of the lecture, the von Neumann entropy is always bounded above by the thermodynamic entropy. There's a subtlety, however, which is that in general there might be multiple extremal surfaces between the left and right boundaries of the figure. According to Ryu and Takinagi, in that case, the von Neumann entropy is the area of an extremal surface of minimal area that separates the left and right. So a slightly refined version of the statement is that you take not the extremal area but the minimal area, the area of a surface whose area is not just extremal but minimal among all extremal surfaces. Once one realizes one has to talk about minimal area, it becomes clear there might be a phase transition in the location of the Ryu-Takanagi surface. As a black hole evaporates, there might as a black hole evaporates, might be a phase transition in the location of the minimal surface that represents the von Neumann entropy. Just such a phase transition in the field of an evaporating black hole was found a few years ago and resolved some of the paradoxes. It doesn't matter, I'm almost finished. Okay. Just such a phase transition was found just a few years ago and resolved some of the paradoxes that arise in trying to reconcile the thermal nature of the Hawking process with quantum mechanical unitarity. I thought about trying to describe their work. I decided it would be a little bit too much. I would have had to explain exactly what version of the paradox they settled, and I would have had to talk about the quantum corrections to the Ryu-Takanagi formula. I thought it was too much to fit into one colloquium. But at least from what I've said, it's clear that it wasn't clear until 2019 to very many people, but it's clear that we should worry about phase transitions in the quantum extremal surface, and worrying about it has proved to be very important. But there's still much to do to more fully understand whatever black hole thermodynamics is telling us about the fundamental nature of quantum mechanics and gravity. A full understanding of the evaporating black hole, or possibly of similar puzzles in cosmological models, may yet reveal deep secrets about the quantum nature of gravity, of geometry. The story that began with Bekenstein and Hawking more than half a century ago may still have a long way to go. Thank you.
Yeah. We have time for a few questions. Okay.
When you ask what kind, it's a discontinuous phase transition, like a first-order phase transition. So there are two extremal surfaces in different places in space-time. As the black hole evaporates, their areas change continuously, but you make an abrupt transition from this one having less area to this one having less area. So it's analogous to a first-order phase transition in thermodynamics.
Other questions? If not, I have a question.
Yes.
What about a maximally rotating or maximally charged black hole for which there is no bifurcation surface? In that case, how would you generalize the reasoning that you just exposed?
Well, I'm not sure. I'm not certain what aspects you want me to generalize. So there's the Ryu-Takanagi surface.
Yeah.
I'm motivated by considering a particular geometry, but that wasn't the starting point of Ryu and Takanagi at all. So the setup, the Ryu-Takanagi story is general. So it makes sense for the extremal black holes. But I might tell you that there's been a lot of significantly better understanding of extremal black holes. So it's now understood that in the absence of supersymmetry, there aren't really extremal black holes quantum mechanically. The classical picture breaks down near zero temperature. And, okay, well, I think we're getting to too much of a digression. I think the best answer to give you is simply that I motivated the Ryu-Takanagi formula with a particular type of geometry. Okay, there are more general discussions.